Arizona, Chicago, and Michigan, and is a faculty member at Rice University since 2019. So he has been working a lot on, I think, on electroweak phase transition and phase transitions and Higgs physics related to that. But today he will be talking about something else, about X-ray signatures of axion emission from compact stars. So, Andrew, please.
Thanks very much, Michael. Yeah, I have spent a lot of time thinking about physics of the electric phase transition. I'd certainly be happy to chat about that also after the talk. I have time. But I've noticed, looking at your calendar of talks for CPPC for the next few months, that it's very Axion heavy, and I think that's indicative of a growing interest in this topic more generally. So I feel like I'll try to kick off your seminar series in discussions of axions for the next few weeks. So what I want to tell you about is some work I've been doing for the last few years using astrophysical observations of compact stars, white dwarf stars, and neutron stars as a probe of axions. And the question I want to be thinking about, at least for the first part of this talk, is the one shown here. Do white dwarf stars generate hard X-rays? And by hard, I'm referring to energies above a few keV. And now the answer to this question is simply that we don't know. These types of stars are not supposed to be creating hard X-rays at energies above a few keV. But the reason we don't know if they do is because we haven't checked. And nobody's bothered to check because nobody expected them to be generating hard X-rays. But what I want to try to convince you of in the rest of the talk is that measurements of these stars in X-ray could reveal evidence for hypothetical particles called axions. And the idea is quite simple. Many years ago, or for many years, people have been thinking about the creation of axions at the core of stars like our sun and other compact stars. And the emission of these axions can induce an X-ray signal as the axions pass through the star's strong magnetic field. So if we were, which is what I'll describe in the course of the talk. And so if we were to measure that X-ray flux with a telescope here at Earth, like the Chandra X-ray Observatory, this could provide compelling evidence for the existence of axions in nature and evidence for their coupling to matter at the core of these stars. And in fact, after we put our paper out a couple of years ago on this topic, the first in a series of papers that we've been working on, we put in a proposal to the Chandra X-ray telescope. They were asking astronomers and astrophysicists for suggestions of what should they spend time staring at with their X-ray telescope, and we recommended them to stare at my new favorite star, REJ031783, which is a highly magnetic white dwarf star that we identified would provide a promising candidate for these axion-induced X-ray signals. And so the proposal was accepted last year, and then the actual observing was delayed because of COVID. But they finally got around to spending some time looking at my favorite star in December, I think, and we were given the data in January, which we're investigating now. So I won't be talking about the results of that data analysis, but the paper will be forthcoming in hopefully the next month or two. But what I do want to tell you about is what types of physics we might learn about, the physics of axions, from these types of X-ray observations of magnetic white dwarf stars. So here's the plan for the talk. I saw from the CPPC website, and I was just talking with Michael about some impressive number of students as part of this group. And so I wanted to start by clarifying what is an axion and what role does it play in fundamental physics? What purpose does it serve? So we'll spend a few minutes talking about the physics of the axion, but really what I want to get into is how would the existence of axions in nature lead to X-ray emission from magnetic white dwarf stars? And what can we learn about axions from observing these types of stars in X-ray? And if time permits, there's one other topic that I wanted to discuss, some other ongoing work about X-ray emission from not white dwarf stars, but rather a particular set of neutron stars, how an X-ray emission in these systems could also be attributed to axions produced at the core of the star and their couplings to muons. So I'll start by providing a brief introduction to axions. Let me say before I forget, if there are questions or comments at any time, or if you'd like me to slow down or clarify, don't hesitate to stop and interrupt me. That should be perfectly fine. So I wanted to provide a bit of a heuristic understanding of what problem does the axion solve, rather than going through a more rigorous, introduction from just writing down the Lagrangian. So we'll talk about axions and motivate them from a somewhat of a cartoony understanding, but it gets it fails in some regards to accurately describe nuclear structure, but it gets the main physics points across. So in trying to understand why we need an axion, it's useful to think about a property of the neutron's electric dipole moment. And for that purpose, we can develop a very crude model for nuclear structure in which the neutron can be thought of as just build up from 3 quarks, an up-type quark with charge 2/3 and a pair of down-type quarks with charge -1/3, localized into some region of space that's about as big as a Fermi. So if you were to ask an undergraduate student to estimate the electric dipole moment of this system, the typical scale of electric dipole moment could be estimated by just taking the product of the typical charge and the typical length scale to infer a typical electric dipole moment at the level of 10⁻13 e centimeters. Now, for many years, we've attempted to measure the neutron's electric dipole moment and never succeeded at doing so, but rather we've placed extremely strong and impressive upper limits on the magnitude of the neutron's EDM at the level of 10⁻26 e centimeters, meaning that our naive estimates were too large by 13 orders of magnitude. And that's a big problem. Evidently, something about the nuclear structure is very peculiar, leading to an electric dipole moment in nature that's at least 13 orders of magnitude smaller than you would not have naively expected. Now, of course, the naive estimate is based on considering a generic configuration of the 3 constituent quarks. You may have already noticed that there's a special configuration for the 3 quarks in which I can make the electric dipole moment arbitrarily small. So if I imagine lining up the 3 quarks with the up quark in the center and the 2 down quarks equidistant on either side, then the electric dipole moment would vanish, since I have to take a vector sum of all of the charges and their locations. Or if I allow for a deviation away from that configuration parameterized by an angle theta bar, for an arbitrarily small theta bar, I can obtain an arbitrarily small electric dipole moment. And then the experimental limit that I mentioned on the previous slide translates into an upper limit on the magnitude of theta bar at the level of 10⁻11. So I'm not claiming, of course, that neutrons are modeled very well by 3 quarks sitting in a line. That's a shortcoming of this crude model for nuclear structure, but there is something about this crude model of nuclear structure that does carry over to the more accurate description, which is the fact that the small neutron electric dipole moment is associated to an enhanced symmetry. If I imagine having the 3 quarks actually sitting on a line, that special configuration of the quarks has a parity symmetry under which all the particles are reflected across the origin and the configuration is left unchanged. So what we're learning from the crude model of nuclear structure is that the data is telling us that this structure of the neutron exhibits a very nearly approximate or possibly exact parity and also charge conjugation symmetry, CP symmetry. Now, in order to understand where the axion fits in, we need to know one more fact about this parameter theta bar that's controlling the CP violation in the nuclear structure. What we need to know is that having a non-zero theta bar costs energy. This is a result that could be derived from thinking of a dilute instanton gas associated with QCD instantons. The idea being that if theta bar were equal to 0, which is the configuration with the enhanced parity symmetry or CP symmetry, that configuration, that value of theta bar would cost, say, 0 energy. But as I start increasing theta bar from 0, I have an associated energy cost that's growing like cosine of theta. Now, the fact that the non-zero theta bar costs energy provides an avenue for solving the problem associated with the tiny neutron EDM. If we were able to promote the parameter theta bar to become a dynamical variable, then that variable would tend to evolve so as to minimize this energy function. And since the minimum of the energy function coincides with the special symmetric configuration where the CP symmetries are stored, the dynamically evolving theta parameter would naturally solve the problem of why theta is so small. It would provide a dynamical explanation for the smallness of CP violation, QCD. And now this is precisely where the axion comes in. The idea, now we're coming back, of course, to Lagrangians, in which the parameter theta bar was introduced as the QCD vacuum angle. It's a fundamental parameter of nature, but the coupling of a pseudoscalar field A to QCD field strength tensors acts like a effective contribution to the vacuum angle when this field acquires a VEV. And the entire combination in parentheses then is the one that costs energy, such that if the axion field is allowed to evolve in time, it'll try to evolve so as to set the quantity in parentheses equal to 0. And as the quantity in parentheses, that's controlling the magnitude of the neutron EDM. So in this way, the axion provides a solution of the neutron EDM problem, or also known as the strong CP problem, explaining why CP is such a good symmetry in the QCD sector. But of course, in addition to just providing a classical background, A also experiences quantum excitations as pseudoscalar particles. And the properties of these particles are then, of course, the same as for any other pseudoscalar field. The particle has spin 0, it's on parity, and in particular, it carries no electric charge or color. Now, the absence of electric charge and color make the axion a particularly challenging particle to test directly in the laboratory. Also, this decay constant is the scale of symmetry breaking associated with the Goldstone A. We typically expect it to be quite high, so maybe it's on the order of 10 to the 12 GeV, just to give a ballpark number, but it can float around by a couple orders of magnitude, which makes the couplings of the axion, especially the non-electromagnetic and non-colored couplings of the axion, especially weak. Now, evidenced as in part by your own seminar series and the lineup of talks you're expecting to have in the next few months, there has been a growing interest in axions in recent years. Part of this has been the renewed perspective on the role of these particles. Rather than thinking just about axions whose job it is to solve the strong CP problem and explain the tiny neutron electric dipole moment, one can think more generally about axion-like particles, which are also light weakly coupled pseudo-Goldstone bosons, but whose job it is, who don't play any role in explaining the neutron EDM. And these types of axion-like particles arise generically in many of our favorite theories, even string compactifications. One from a perspective of the low energy perspective, a string theory is expected to have many scalars and pseudoscalars in the spectrum associated with the size and shape of the compactified dimensions. And there's also been a lot of interest in the role of the axion or axion-like particles as dark matter. I'm not going to be assuming that the axion is dark matter, but it could be. It doesn't change the story I'm going to tell. So from this effective field theory standpoint, when we're thinking about axion-like particles, we would write down a Lagrangian like this one, where here I just have three parameters: the axion's mass, a coupling that controls the axion's interaction with photons, and a coupling that controls the axion's interactions with electrons. But of course, even in the EFT, one would write down many more operators coupling to muons, for example. Or if you're interested in physics at the scale of colliders, for example, you'd think of couplings with Z's and other particles. As I mentioned a minute ago, these couplings are expected to be very small, since the scale of new physics is associated with the Pecha-Quinn symmetry breaking, which is, we may have in mind to be 10 to the 12 GeV, for example, but as I said, it can go up or down a couple decades. But it's these tiny couplings with ordinary matter that makes the axion particularly challenging to probe in the lab. So these beautiful plots made by your own Karen O'Hare, I think wonderfully characterize the situation with searches for axions. I'm not going to talk about each of the individual exclusion limits here, but I just want to draw your attention to the fact that there's a variety of different experiments and experimental techniques being used to search out the axion through its various points of interaction with the standard model. So in the context of coupling the axion to photons, we've got laboratory searches, astrophysical searches, cosmological limits. All of these have been used to try to identify the axion in nature, and having not found an axion yet, we produce exclusion curves shown over here. And similarly, in regard to the coupling of the axion to electron, a mix of laboratory limits and astrophysical limits show the variety of techniques being used to look for axions. Another way of highlighting the growing interest in axions is to look at the citation counts for the original paper by Pecha and Quinn, which has this exciting rise in recent years, in the last decade or so. Every year, almost more citations than the last. And I think it's nice to actually see a rising curve like this that we can think of in a positive light. In the US, we've been seeing rising curves like that for many months now, but they come along with not a sense of excitement, but rather anxiety and dread of where this curve might end up going. So on the left-hand side, on the other hand, I'm completely happy if this citation count curve continues to rise exponentially. So that's what I wanted to say by way of why I think axions are a particularly compelling target. What I'm going to be talking about now is a novel astrophysical search strategy for trying to identify axions in nature. When I say axion, just as a matter of language, I'm referring, I really mean axion-like particle. I'm referring, I don't care if this particle is solving the strong CP problem. That's not relevant to what I'm going to do. It would be, well, all that's really relevant is the particle I have in mind here is a light pseudoscalar, and it couples to electrons and photons. So the next couple parts of the talk are going to be astrophysics-y. And when I started working on this a few years ago, I had to spend a day on Google reminding myself what a white dwarf star is and how big they are and what other facts we know about them, since as Michael said in the introduction, my research in past years has been focused more on early universe cosmology and electric phase transition. So let me give you a bit of that data dump on what is and is not known about white dwarf stars. So we're thinking of a category of star that started their life as solar mass, intermediate mass, but have now grown very old and exhausted their nuclear fuel, so they're no longer fusing. And instead, they've cooled down and collapsed at a much smaller size. The mass of these stars can still be up to solar mass, but it can also be smaller by a factor of a few. And the size of these stars, though, is more like the size of our Earth, so about 1% of the radius of the sun. And not having the fusion to support the star, it collapses under its own weight by gravity. And also the star tends to be a lot dimmer than our own sun. So typical luminosities are maybe in the ballpark of 1/10,000th of a solar luminosity. Now, what's interesting is that the magnetic field strengths, on the other hand, can be quite large, and this makes sense. Our sun has a magnetic field strength of about 1 Gauss, and if you take a big star with a magnetic field of 1 Gauss and allow it to collapse to a star 1/100th of the size, conservation of magnetic flux requires the field strength to grow, and so the field strength for these white dwarf stars can be as big as a megagauss or 100 megagauss, say. It's not as large as neutron stars. So a magnetar, on the other hand, since it's even smaller, about a radius of 10 kilometers, would have a magnetic field strength of 10 to the 12 or 14 Gauss. So we're not talking about magnetic fields as strong as neutron stars here, but we're still talking about extremely strong magnetic fields. These stars are predominantly composed of degenerate electrons. Now, if the star were only electrons, it would have a negative total electric charge. So there's a compensating number of nuclei, often carbon and oxygen, floating around in order to ensure that the net electric charge is vanishing. The structure of these stars tends to be very homogeneous, so that thermal conductivity is extremely high, so you can think of this degenerate core as extending almost out to the edge of the star. And then at the edge of the star, where the density is dropping, the electrons are no longer degenerate, and there's a region known as the atmosphere that makes up about the last 1% of the surface of the star. Now, how many of these stars are there? The closest white dwarf star to Earth is Sirius B. It's about 8.6 light years away, so it's fairly close. And in fact, we don't know how many white dwarfs there are in the Milky Way as a whole, but we expect that most of the stars in the Milky Way are actually white dwarf stars, just because these are the end states of typical stellar mass stars. The bigger guys would go supernova, but the smaller guys can become white dwarfs. And this galaxy is old enough to the point that we think that there can still be lots of white dwarfs around. So this provides an exciting opportunities for the types of measurements I'll be talking about, looking for X-ray signals from these stars. Now, the idea of getting axions from stars, white dwarf stars or neutron stars or even our own sun, is certainly not a new idea. It's been discussed at length for many years. One of the ways in which you make axions from a white dwarf star is through electron-nucleon bremsstrahlung, where the axion can couple couple to the electron. And the expected luminosity in axions then is at the level of 10 to the minus 4 solar luminosities if the axion-electron coupling were around 10 to the minus 13, if the mass of the star were around a solar mass, and if the temperature at the core of the star were around 10 to the 7 Kelvin. So the parametric scaling should make sense. The luminosity which is the energy output per unit time, should go like the cross section, which goes like the coupling squared. It also, luminosity involves an integral over the entire star, all the emission volume. That brings the factor of the white dwarf mass. And the core temperature sets the density of an energy available to the scatterers, which brings the factor of core temperature to the fourth. So when we think about these compact stars like white dwarfs, they may be glowing dimly in photons, but we should also imagine that they are glowing as well in axions. And the spectrum of these axions is essentially thermal, set by the core temperature of the star, so around 10 to the 7 Kelvin. 10 to the 7 Kelvin, by the way, is around 10 keV. So it's a thermal spectrum that peaks at around 10 keV. Now, the fact that compact stars can emit axions provides an avenue for constraining. Well, it provides an avenue for testing axions, but the absence of, let me put it this way. If the axion were to couple too strongly to electrons, then the star would be producing too many axions and losing too much energy through this axion emission. And we have some understanding of how white dwarf stars are supposed to cool down just due to photon emission or neutrino emission. And if they seem to be cooling down more quickly, that provides a constraint on the axions coupling to matter. So this is usually, in the context of white dwarfs, this is usually expressed in terms of the white dwarf luminosity function, which is a measure of the number of stars for a given brightness. So I'm showing a plot over here. The horizontal axis is a measure of the brightness of the star. The vertical axis is a density of stars for a given brightness. And the data points show the measured white dwarf luminosity function taken from, as presented by this group. Now, what is the effect, what is the prediction, and what is the effect of increasing the size of the axion coupling to electrons? So if the axion did not couple to electrons, if we set GAEE to 0, we would have this top curve shown here. And as we start increasing the strength of the axions coupling to electrons, the prediction shifts down to here because the stars are starting to exhaust more of their energy in the form of axions. Now, this plot, in making this plot, the group assumed a relationship between the axion mass and the axion electron coupling, which one need not assume. That's a specific model. So although they're talking about increasing the axion mass as you move to these lower curves, we should really be thinking of that as just increasing the axion electron coupling. So obviously, if the axion electron coupling were too large, I would start to come into conflict with this data. And these types of arguments have led to an upper limit on the size of the axion electron coupling at the level of 3 × 10⁻13, which is actually the strongest limit on the axion electron coupling for low mass axions. So simply by these indirect observations of white dwarf cooling being consistent with the standard predictions, we already learned something about axions and how they couple to matter if they exist. Now, beyond the cooling limits, a variety of measurements in several different astrophysical systems have suggested the possibility that there might be more cooling than the standard cooling channels would allow. And these observations have been made not only with white dwarf stars, but also bigger, hotter stars like red giant branch and horizontal branch. And so this this article summarizes the favored parameter space if you interpret this anomalous cooling as resulting from the coupling of axions to matter. And they find that there's a 2 to 3 sigma preference for a non-zero axion electron coupling at the level of 1.5 × 10⁻13 electron volts, and a pretty weak preference for a non-zero axion photon coupling. So what I'm going to be talking about isn't assuming this cooling hint to be true, it could certainly be the case that either this is, it could be, and lots of things could be the case about whether this is statistical fluctuations or really new physics or some unknown astrophysics. But I think what's important is that this provides an interesting target for future observations. We'd like to have some orthogonal way or complementary way of probing this favored parameter space and testing this idea that axions are responsible for the anomalous cooling. And that's where the X-ray observations that I'm going to be talking about will come in. So let's ask ourselves, suppose that we believe that axions are responsible for this anomalous cooling observed in these different astrophysical systems. How would I test that? What other measurement could I make? So one thing you might try to do is detect the axions, right? I mentioned that when we think of compact stars, we should be thinking of them not only glowing in photons, but also glowing in axions. And I've got axion detectors around on Earth. I mean, I don't personally, but there exist axion detectors on Earth trying to detect axions every day. So can we use one of these axion detectors to identify the axions that are supposedly being produced by compact stars and making them cool off too fast? So let's do some rough estimates to see if that might work. So I already gave you a formula for the axion luminosity. This is the energy output into axions per unit time by the star. And if I want to know the flux of axions reaching Earth, I'll take the luminosity and divide by 4 pi times the distance squared. So that gives me an energy per area per time. And remember, the distance to white dwarf stars is maybe 10 parsecs away. Now, when the axions get to Earth, how am I going to detect them? So it's there's a well-established strategy that many of the axion detectors on Earth are employing to try to identify axions. And this is the fact that an axion, when exposed to a magnetic field, has a probability of converting into a photon. This is a consequence of the axion's coupling with 2 photons, if such a coupling exists. So if I were to fill a region of my lab, not that I have a lab, but if one has a lab and a detector, and you've got a region of length scale L, and you can fill it with a magnetic field of strength B, and you let the axion traverse that distance L, then there's a probability of the axion converting into a photon, which is given by the coupling squared, the B field strength squared, and the distance squared. This calculation follows similar to doing neutrino flavor oscillations. We're doing essentially a mixing of the axion and the photon, just like you would do this similar calculation for the mixing of different neutrino flavors. Now, all we have to do is put the factors together, the axion flux reaching Earth, the probability of converting axions into photons in a lab, to find the flux of these photons. And the flux is then estimated to be something like 10 to the minus 31 ergs per centimeter squared per second. Now that number might not have much meaning to you. It didn't have much meaning to me the first time when I did this first estimate first. So let's put it into something a little bit more reasonable. If we suppose that each axion has an energy which is around the core temperature of the star, then this corresponds to something like 10 to the minus 18 counts per second, if your detector is maybe a meter by a meter. That's a very low count rate. That's less than 1 count per age of the universe. And so I don't think you're going to get funding to run that experiment. To make this estimate, by the way, even though the predicted flux is incredibly tiny, I was actually kind of generous in choosing fiducial parameters. So I put the white dwarf star essentially as close as can be, 10 parsecs away. I assumed that my experiment was a whole meter big, which is quite big, and I assumed that I could fill it with an incredibly strong magnetic field of 5 Tesla. And then I maxed out the size of the couplings. Right? We already talked about how the axion electron coupling is known to be less than 10 to the minus 13 or so from these white dwarf cooling observations. And it turns out that direct observations the Axion photon coupling is also known to be smaller 10 to the minus 11. So these are the maximal values for the couplings. And even at that point, I'm getting a tiny flux. So evidently, this strategy of producing axions in the white dwarf star and just waiting for the axions to reach Earth where I might detect them is not a good way of testing the idea that axions are emitted by the star. Are there any questions? I can't see the chat, but I saw a little one pop up over here, which might mean there's a question.
Yeah, I have a quick question maybe. So this is for a single white dwarf star, but you're mentioning that there are 97% of the stars in the galaxy are white dwarfs.
Right.
If you added up the kind of diffuse flux from all of the white dwarfs in the galaxy, would that make up those orders of magnitude that you need, or would you end up with kind of a similar estimate? Because I guess that maybe, you know, you're only going to be sensitive to the most closest ones because of this 1/d² fall off.
Yeah, that's a great question. So I think you also partly answered the question yourself. So the further away guys are going to contribute less because of the flux factor. But moreover, even if I suppose that all of the stars in the galaxy were 10 parsecs away from us, we push all the stars into our local neighborhood, there's, what did Carl Sagan tell me? There was billions and billions of stars or something in the galaxy. So that would take me maybe from 10 to the minus 18 counts per second up to 10 to the minus 9 counts per second, which would still be, you wouldn't have to wait a whole age of the universe, but you'd have to wait a really long time until you started getting a signal. So even that case wouldn't help all that much. Are there any other questions?
Yeah, there's also one in the chat. I'll just read it out. It's someone's asking about if the T on the BT means transverse, so the transverse component of the magnetic.
That's right. Yeah, that's right. I'll actually do this conversion calculation for you guys in a couple of minutes in some more detail. Anything else? Now, all right. So we don't want to wait until the axions reach Earth to try to detect them, but in fact, we don't need to wait till the axions reach Earth to detect them. I just got done telling you how compact stars like neutron stars and white dwarfs can have incredibly strong magnetic fields of their own. This provides an opportunity of accomplishing that axion photon conversion in the environment of the host star. And this is an idea that's been, this is actually an old idea proposed first by Donald Morris in the 80s. And it's received a lot of renewed attention in recent years by several different groups in the context of looking for axions from magnetars or dropping axion dark matter onto compact stars and producing electromagnetic radiation in that way. So the basic picture now, to extend my cartoon a bit, is shown here. We'll imagine electron nucleon bremsstrahlung produces an axion through the axion electron coupling. And then as that axion is leaving the environment of the star, the strong background magnetic field leads to a conversion of the axion into a photon. And this photon is now an X-ray photon. So the energy of the photon is tied to the energy of the axion. The energy of the axion is tied to the kinetic energy of the scatterers, which was the core temperature of the star, which is around 10 keV. And so this 10 keV-ish, 1 to 10 keV-ish gamma ray, X-ray, sorry, now leaves the environment of the star and hopefully propagates its way to a X-ray telescope here on Earth. One thing that makes this, this strategy particularly interesting is that you might ask, don't these stars already produce X-rays? And I'll come back to this issue in a couple, I don't know, 10 minutes or so. But in fact, in this high energy band from a few keV up to maybe 10 keV, this isolated white dwarf star is not expected to produce any hard X-rays, meaning bigger than a few keV. And we'll talk about that in a bit more. But in other words, there's a sense in which this is a zero background search. If you see anything from these white dwarf stars at these energies, something funny is going on. All right, so now there's a slightly technical set of slides, but it comes to this question of the Axion photon conversion. So what I want to get at is just calculating the signal of that X-ray spectrum leaving the star. And the calculation of the Axion luminosity, as I mentioned, was done by, worked out in the 80s. So what we need to work out here is the probability that the Axion will convert into a photon. And I thought this group might find it interesting because I know there's people thinking about neutrinos and neutrino flavor oscillations, and the calculation here is very similar to that one. So I thought I'd just give you the flavor of how it goes. So we're thinking of this interaction between axions and photons with a coupling GA gamma gamma. Writing out the field strength tensors gives this 3-particle interaction, but in the presence of a background magnetic field, I'll put this guy on the background, and now that interaction has become a 2-particle mixing. So this is what's going to lead to axion into photon conversion. It's also important to keep track of the fact that photons have a quartic self-interaction that you can understand resulting from integrating out the electron and drawing a box graph. This will be important because here I have 4 factors of the field strength tensor. 2 of them I'll set to be the background magnetic field, and the other 2 then modify the photon's dispersion relation. So I get a magnetic field dependent modification to the photon dispersion relation. That'll play an important role in a couple minutes. So from this Lagrangian, we derive the field equation. We make a Wkb approximation, which lets us neglect the second derivative terms. We have a first order equation like a Schrodinger equation for the wave functions of the different fields. And we'll keep our eye here on these off-diagonal entries. These are the ones proportional to the axion-photon coupling and the background magnetic field. These are the ones that are responsible for the axion-photon mixing and the axion-to-photon conversion. So now I'll solve these equations, but first let's make some simplifying assumptions about the background magnetic field itself. So as a first simplification, let's suppose that the background magnetic field is isotropically oriented along the path of the axion. We don't have to do this for the numerical analysis, but it gives us a nice analytic solution to discuss. That's convenient because now I can use the magnetic field orientation to choose my basis for the photon field. And my 3x3 matrix block diagonalizes into a 2x2 matrix, where the axion now is only mixed into the component of the magnetic field parallel to A. This is where the B transverse enters. And again, the off-diagonal entries are proportional to the axion-photon coupling and the magnetic field strength, so they're what's responsible for the mixing. Now, in reality, the strength of the magnetic field as we leave the star should be falling off, because obviously if I'm far away from the star, the magnetic field gets weaker. But to have a more familiar calculation, let's suppose, just for the sake of discussion for a minute, that the strength of the magnetic field were just constant for some finite distance outside the star. So maybe from the surface of the star up to one more stellar radius away, we have a constant magnetic field, and then the magnetic field is just 0. In that configuration, the differential equation on the previous slide can be solved analytically, and we get a solution that looks like this for the axion-photon conversion. I should say that the axion-photon conversion probability is just defined as the squared amplitude of the photon field finally, well, the final squared amplitude of the photon field over the initial squared amplitude of the axion field. That's how you get the probability from the solutions of the equations in the previous slide. And now this equation has a familiar form to those who have studied neutrino flavor oscillations. We get the sine squared of a mixing, which was coming from that off-diagonal element in my 2x2 matrix. And we get the sine squared of an oscillation length and a distance where, as I said, the magnetic field fills a region of space equal to 1 stellar radius. And in fact, this is a nice formula because we could plug in some numbers and make a plot, but it actually does quite a good job even for compared to, it's a reasonable approximation. It's a good approximation to the full answer. But we can do a bit better. As I said, the magnetic field strength isn't just constant outside the star. The magnetic field strength falls off with distance away from the star. And if we think of the star as a magnetic monopole, the field strength would fall off like r to the -3. So if we put that into the equation, we end up getting an analytic solution shown here. And now it's defined in terms of some special functions like this generalized Euler gamma function, but it has some features that we would expect. For instance, that off-diagonal entry in the mixing matrix shows up in the front. So if this guy were to vanish, then the probability obviously would vanish as well. Since this formula is harder to digest because of the special function in here, let's just make a plot of it. So here I have the exact same formula as on the previous slide, and I'm going to present a plot. On the horizontal axis, I'll vary the strength of the magnetic field, and on the vertical axis, I'll show the value of the Axion photon conversion probability scaled up by 10,000. If the magnetic field is weak, then as I increase it, the probability grows like b squared. And this is exactly what you'd expect from the fact that the off-diagonal elements in the mixing matrix are proportional to b, and my probability should go something like sine squared 2 theta. So that would go like mixing angle squared, so that would go like b squared. But actually, once the magnetic field becomes strong enough, that b squared growth turns over to just a b to the 2/5 growth. Now, why does this happen? This happens because there's also an entry in my matrix on the diagonal that grows with increasing b. So if we come all the way back over here, this on diagonal entry for the photon also increases with increasing b. This is the effect of that Euler-Heisenberg 4-photon self-interaction. So as I increase the magnetic field strength, I'm making the off-diagonal elements bigger linearly, but I'm making this element on the diagonal bigger quadratically. And the effect of that is that I still gain probability with increasing field strength, but I only gain like b to the 2/5 power now. So this is one important, this behavior is important because you might think that if I'm surveying all known white dwarf stars, it's absolutely critical for me to find the one with the strongest magnetic field. But in fact, the guys with the strongest magnetic fields, they all live over here in this region in this part of the parameter space. And going from 100 to 200 field strength actually doesn't gain you that much in conversion probability because of the suppression due to the Euler-Heisenberg photon self-interaction. So it's not absolutely essential to find the strongest magnetic field available. All right, that was the long technical aside. Let me just sum up this, and then we'll move on to talk about specific stars. So just to sum up, Axion emission has the total luminosity was given by a formula I presented a few, 5 or 6 slides ago. And the spectrum is nearly thermal, so we're just bremming axions off of a non-relativistic population of electrons and nuclei. And then the corresponding flux of X-ray photons that are produced is given by that Axion luminosity spectrum, the Axion photon conversion probability, which has a very weak energy dependence in this energy interval, and divide by the geometrical factor. So just to give you a picture to have in mind, this blue curve would show the Axion spectrum for some fiducial parameters for the star and the couplings. And this red curve would show the corresponding X-ray spectrum. It's peaked at around a few keV because the core temperature of the star that we're considering for making this plot was around 10 to the 7 Kelvin, which is around 10 keV. And the spectrum is continuing to rise through the few keV energy interval, which is unusual. All the backgrounds, as I'll also discuss shortly, are actually falling in this region. All right, so, okay, I'm already running short on time. This is the end of the discussion about the actual signal. Then I wanted to talk a little bit about just surveying the known white dwarf stars and deriving limits. So were there any other questions about the calculation of the signal itself?
Can I ask one question? Can you get a resonant conversion? Kind of like for neutrino oscillations, you also get resonances in there.
Yeah, right, that's great. So in the context of, you can get resonances in the context of axion dark matter falling onto the star. I don't think you can get resonances in the context of what I'm talking about, where I'm making axions in the star. But this paper, for example, studied cold axion dark matter being dropped onto a neutron star. And the energy that the dark matter comes in with is just its mass, because it's non-relativistic. And there's a medium around a neutron star with a non-zero plasma frequency. So at some point, as the axions are approaching the star, the axion's mass will match to the plasma frequency, and then you get a resonant conversion because the on-diagonal entries become small. And then their result is that you get a line-like spectrum. But that doesn't happen for that can't happen for the calculations I'm doing, because I'm making axions inside the stars. Its energy is much higher.
Okay.
Yeah,
Thanks.
that's a good question. Anything else?
Yeah, on a kind of similar note to that, I mean, if the interior of the white dwarf is magnetized, could you have a kind of resonant conversion of like the plasmons inside the star? Or would the flux of that just be kind of too tiny because you're relying on the magnetic field and the photon?
Yeah. Well, okay. So if the conversion happens inside of the star, the X-ray would not escape. So the star is opaque to X-rays, whereas the environment around the star is not opaque to X-rays.
Okay, yeah. Sorry, I'm thinking of it in the opposite direction, where you have the axions and then you convert them back into photons in the detector. Yeah, sorry. Yeah, you were saying you would, if for that to work, you'd have to then have them convert again, which is then you're suppressing another factor.
Yeah. But that's an interesting question too. Yeah, or even, I mean, I don't know. Maybe in the atmosphere, this outer region of the white dwarf, maybe there it's transparent to X-rays, but you could still have some plasma effects. But I haven't thought about that. Anything else? All right, let me pick it up a bit. I think at this rate, we're not going to get to section 4, but that's okay. But I'll try to finish up section 3 as quickly as possible. I don't want to keep people too long. Now the question is, all right, are there any known stars that we should be looking at to identify this X-ray signal? So the Gaia survey has endeavored to map out all of the nearby white dwarf stars within 100 parsecs of Earth. Their current catalog contains already 70,000 white dwarfs. So you could think of each of these guys as a candidate for the types of X-ray observations that I'm talking about. Now it's easy to, it's not easy to find white dwarfs. They're quite dim. So you actually can't find all of them throughout the whole galaxy. We'll only find the ones nearby. But finding them just means seeing their light and measuring a spectrum, or just seeing their light. But you don't necessarily measure a spectrum, and you don't necessarily learn about the strength of the magnetic field. We expect that all of these 70,000 stars are magnetized, but to actually measure the magnetic field requires an additional spectral measurement. And so far, only a few hundred of the known white dwarfs have had their magnetic fields measured. This is because to measure the magnetic field strength, the best technique for doing this is to rely on the fact that the spectrum of hydrogen is split in the presence of a magnetic field due to the Zeeman effect. So this very hard to see graph is showing several different spectra for different stars. This one is inferred to have a 1 megagauss magnetic field. This one's inferred to have a 42 megagauss magnetic field. And the point is that these two spectral features are split further and further as the magnetic field strength is increased. So these are the types of spectral measurements used to infer the magnetic field strength. And we have at least 300 to 500 or so for which those measurements have already been made. So out of that catalog of several hundred known magnetic white dwarfs, I can do a calculation of the corresponding X-ray flux for each of them for some fiducial mass and couplings, and rank them all. And the most promising candidate is this one I've mentioned at the beginning, REJ031753, which is not too far away. It's about 30 parsecs away. It's the closest of all the top 10 on the list. It doesn't have a particularly strong magnetic field. I mean, it's a strong magnetic field, but it's not the strongest in the list. But that's okay because of the b to the 2/5 growth that we mentioned before. It is quite big and it is quite hot. And being big and being hot do help because even the Axion emission from the star grows like the magnetic field to the 1st power and the temperature to the 4th power. This star, REG 03753, is special. It's been recognized for years as the hottest known highly magnetic white dwarf. And it was first observed in soft X-rays, meaning sub keV energies, maybe sub half a keV energies. And it was also measured in optical and far UV, which is how we learned about its magnetic field strength. And in fact, one interesting thing about this star is that there are measurements of phase-resolved spectroscopy, meaning that as the star spins around over the course of 11 minutes, we can watch the spectrum change. And that means that we're not only learning the magnetic field strength of the star, but we're learning about the magnetic field structure. Is it a magnetic dipole? Is it a magnetic dipole that's turned this way or that way? We can infer that information from looking at these time-varying spectra. And since the star was so special, it was the hottest known highly magnetic white dwarf. There was an attempt made to observe it in hard X-ray, meaning energies above half a keV or so, which is somewhat unusual. And the Suzaku telescope spent, I think this is 20 hours or something, staring at it. And they did not observe any hard X-rays, and instead they placed an upper limit on the X-ray flux. But I can use that as I can recast their upper limit on the X-ray flux as an upper limit on the Axion coupling to matter using the calculation I presented before. So here's the main result from a paper a couple years ago with Ben Softy and his student Chris Desert. We're showing the parameter space of Axion mass on the horizontal axis, and on the vertical axis, the product of the Axion photon coupling and the Axion electron coupling. Remember, we need both, one of them to make the Axion at the core of the star and one of them to convert it into a photon outside. And that upper limit on the X-ray flux from Suzaku can be recast as this upper limit on the parameter space, which notably is 2 decades stronger than the previous best limit on this particular combination of parameters from the cast helioscope, shown here. It's about one decade stronger than if you combine limits on GA gamma gamma and limits on GAEE from different observations. So that was a nice result. Here we're seeing a dramatic improvement in limits on this product of couplings. We're also constraining the part of the parameter space that was favored by those cooling hint anomalies that I mentioned earlier. And moreover, these measurements by Suzaku isn't really the best telescope suited for these types of measurements. Their flux sensitivity isn't as good as other telescopes like XMM Newton or Chandra. So if Chandra had spent a comparable amount of time staring at this star, looking for X-rays, and if they didn't see anything, they would have obtained a exclusion limit shown here. Or to put it another way, if Chandra were to make a comparable measurement with a comparable exposure, they would test all of the parameter spaces in here. I think this is exciting. We're taking chunks out of this ALP parameter space. We're not reaching the part of the parameter space that's favored for our favorite models of the QCD Axion. And I think that fact is probably why there wasn't a more focused effort on making these types of observations earlier when, as I mentioned quickly, this strategy was first proposed by Donald Morris back in the 80s. So at that time, they recognized that this strategy would not be effective at probing the QCD Axion, and I think maybe that's why it wasn't investigated further. But as I said, our perspective as a community on Axions has changed somewhat, and although we are still interested in testing the QCD Axion, in the meantime, we're also interested in testing Axion-like particles that are predicted by other theories and serve other purposes. Okay, now I'm going to start skipping things. This is to tell you that there is uncertainty in the temperature of the star and its composition but when I drew those limit curves on the previous slides, I was doing the most conservative thing. And if you were to do the more aggressive thing, I would have even drawn more aggressive limit curves. And as I mentioned, we put in, and it was accepted, a proposal for the Chandra X-ray Observatory to stare at REJ 0317853, even using a shorter exposure than the Suzaku observation, would lead to, if they don't see anything, it would lead to an order of magnitude improvement in the limit, or even possibly identify some interesting new physics if they do start to see something. And we have that data now, but I'm not going to be talking about it. You should look forward to seeing the paper in the next couple of months, but unfortunately, I'm not going to give you any teasers of how it's going. Okay, let me close by just addressing what would happen if there is a signal, either with Chandra or with some future observations. So suppose that we spend some time with our X-ray telescope staring at one of these white dwarf stars, and we start to see hard X-rays. What are we supposed to make of that? So the first natural question, of course, is could it be astrophysics? And I have been saying this in talks for years, but now I'm going to appeal to authority and just quote a article by the experts, because saying that an isolated magnetic white dwarf star is not expected to have a hard X-ray flux. By hard, I mean, I'm talking, when I say hard, I'm meaning a few keV. I think when astronomers say hard, they probably mean closer to 1 keV or half a keV. There are scenarios in which white dwarf stars can have X-ray flux at a few keV. For example, if the star has a hot companion that's producing X-rays, or if the star has an accretion disk, then these are scenarios in which the star would have a hard X-ray flux. But, and this nice paper surveys some number of stars and identifies the X-ray emission from them, hard X-ray emission from them, but they all have either a companion or they're accreting. And you can tell that there's a companion or they're accreting because there's usually emission in some other band. So if it's accreting, you'd also see emission in the infrared, which you don't expect for an isolated white dwarf. Moreover, if there were really a signal and we wanted to disambiguate or distinguish whether it's a background like this or a signal like this, the fact that the background, it should be falling in this few keV energy band, whereas the signal should be rising, would also provide a way of discriminating the two, if we can make the spectral measurements good enough to tell the difference. So in principle, it could be astrophysics, but you really don't expect, if there were an astrophysical source of the X-rays, you would see other things. You would see the infrared emission, or you would see the companion. Could it be axions is really the exciting question. As I just mentioned, the axions predict a rising spectrum, which is not typical of the backgrounds. The axions would predict ratios of fluxes to be the same across different stars, since it's all controlled by the same fundamental physics, the same couplings to matter. The axion interpretation would predict a time dependence. So actually I have an illustration of that over here. As the star rotates around its axis, the orientation of the magnetic dipole would change. And so the effective strength of the magnetic field observed from here at Earth would grow and decrease. And as the magnetic field strength grows and decreases, the Axion photon conversion probability would also grow and decrease. So if we were able to make such excellent X-ray measurements as to see this time dependence on the scale of the rotation period of the star, that would be further evidence for the axion interpretation. It's correlated with the strength of magnetic field along the observing direction. And also the photons are expected to be polarized, associated with the orientation of the magnetic field. So there's different handles that could be used in the event of a detection to try to discriminate between astrophysical sources of hard X-rays and axions as a source of hard X-rays. All right, well, I think for the sake of time, unless people would like to ask afterward, I'd be very happy to tell you about some of our ongoing work looking at X-rays from magnetized neutron stars and how this provides a probe of the coupling between axions and muons, which is otherwise very challenging to test for. But for the sake of time, I'll skip that. And just sum up by reiterating the main point of the talk. We're proposing to use white dwarf stars as a laboratory for Axion physics. These stars are expected to be radiating axions if the axion exists in nature, obviously, and if it couples to electrons. And what we were pointing out, echoing earlier work by Donald Morris in the 80s, is that that axion could convert into a photon in the ambient magnetosphere of the star and be observed here at Earth as an X-ray. Existing data on a particular star, REJ 03753, leads to the world's strongest limits on the product of the axion-photon, axion-electron couplings for sufficiently small axion masses. But observations that have already been made by Chandra, X-ray Observatory, could improve that limit by over an order of magnitude or test axions living in this part of parameter space here, possibly accommodating these cooling hints. And the work I didn't get to tell you about has to do with axion emission from a particular family of neutron stars known as the Magnificent Seven, in which they're coupling to muons, because of the presence of degenerate muons inside the neutron stars, provide strong constraints on the coupling of axions to this other point of interaction with the standard model. So look out for that paper in the next couple months. All right, thank you for the questions and for your attention.
Oh, thank you very much for a very clear and interesting talk, Andrew. So we have time for more questions. So you can raise your hand or just speak up.
I'll start. Yeah, thank you very much for the nice talk. I was actually exactly going to ask about this Magnificent Seven business, because I think I vaguely remember the original paper on this, and I think your middle plot there, you're ruling out that hint, right? The initial hint that they put on GA gamma GAE with the Suzaku bound. I'm pretty sure that preferred region was above that, but maybe I could be wrong.
Yes,
so is this why you're kind of going to the muon coupling now? Is this part of this story?
Yeah, an astute observation. Yes, so this is a preliminary plot from the work in progress on. Maybe if you let me maybe just quickly introduce the Magnificent Seven story for the rest of the audience. So I've been suggesting that we should look for X-rays from white dwarf stars. Why don't you look for X-rays from neutron stars or magnetars? And you certainly can do that too. They've got even stronger magnetic fields. So you expect even a stronger axion-induced X-ray signal from them. It's a bit trickier though with neutron stars because they can also make hard X-rays. They're a lot smaller, they spin a lot faster, the environment is a strong magnetized plasma. So if you see X-rays from them, it could be harder to discriminate whether they're seeing it, whether it's a new physics result or if it's just astrophysics. This is kind of like, for the collider people in the audience, I like to say this is like the difference between a lepton collider and a hadron collider. So the neutron stars are the discovery machine, it's a hadron collider, but the white dwarf stars are more like the precision lepton collider machine. So this group by Ben Safdie and others, group consisting of Ben Safdie and others, used X-ray data of a family of neutron stars called the Magnificent Seven to search for an X-ray signal. And they claim that in at least two of the stars, they are finding an X-ray signal. And they see that the spectrum is rising, in fact, and they attribute this to an axion. And so they have a favored parameter space for their axion couplings, which is shown, let's say it's shown here. Actually, sorry, let's take, okay, well, in their paper, they cast it as a coupling of the axion to the neutron, because in that case, they're brimming the axion off of a neutron, and the axion-photon coupling is used to convert it into a photon. So they find some favored couplings over here. The limit is independent of the axion mass, because as long as the axion mass is below the temperature at the center of the star, you can emit it without any kinematic restriction. Now, you can also interpret that in terms of axion-electron couplings, right? So I mentioned at the beginning that we think of ALPS as an EFT. In principle, I'm going to let every coupling float independent of every other one. they have nothing to do with one another. But in reality, these theories come down from some KSVZ, DFSC, in the case of the QCD axion or something, will ultimately relate the various couplings. I expect some relation between the axion electron coupling and the axion muon coupling, for example, or the axion electron coupling and axion nucleon coupling, for example. And so if you take the limit that I derived on the axion electron times axion photon coupling and assume the standard relation between the axion electron coupling and the axion muon coupling, then you would infer a limit on the axion muon times photon coupling shown here, which is the Suzaku limit. And meanwhile, the Magnificent Seven observations would have corresponded to a limit shown here. Or I think in terms of this is their limit curve, not their signal detection curve. I guess their signal curve would probably hang out around here somewhere. But as you are expecting, if you do this recasting of the electron limit into a muon limit or even into a nucleon limit, which I don't have here, the Suzaku observation actually is very constraining. There would be a conflict between the parameter space that they favor for their signal and the parameter space that's excluded by the white dwarf observations, if the standard relation between the couplings holds.
Okay, so
what do you make of that?
Yeah.
Mm-hmm.
So it really needs that standard relation between the couplings, kind of that it's proportional to the mass of the.
Yeah, that's what I was about to say. So what you make of that is up to you. You might say that just means everything is flawed and the signal that they saw is not arising from axions, it was just astrophysics. Or if you want to be more generous, you would say that the standard relation between the couplings is simply needs to be different for this axion. There's nothing fundamentally wrong with that.
Interesting. Other questions?
Can I ask just a basic question about back to the white dwarf situation, just about the summary plots you had at the end, either in the conclusion or, yeah, here, exactly. So there's this kind of step feature as you're losing sensitivity at around 10 to minus 543 EV in the mass. What's the physics that's driving that step feature in the sensitivity?
Yeah, that has to do with the axion photon mixing calculation. So that's a comparison of which of these many formulas is a good formula to point at. So, so here's our 2x2 block of mixing matrix, and I'll start out with an on-shell axion. So this entry, I'll set omega equal to root k squared plus m squared, so this vanishes. And then this should have been 0. That's a photon mass, but we'll just set that to 0. We don't need photon mass because it's non-resonant. And then at that point in phase space, this term is essentially the axion mass squared. And I have to compare that term against the the term that results from Euler-Heisenberg. And so depending on which of those guys wins, you get the different parametric behavior. So at really high axion mass, you start to get a suppression of the axion photon mixing, because this on diagonal entry starts being bigger and bigger as the axion mass grows larger and larger. So there's some complicated comparison of those two terms, but that's what led to the weird feature of the bump.
Right, okay. Yep, okay. So you might expect this to be in a different position for white dwarfs with a different strength magnetic field or something like that, because that something that affects the second term in that.
Yeah, yep, that's absolutely right. Yeah, that feature would be star dependent, so it would move around depending on the field strength of the star.
Right. And just another very small question. You said when you were ranking the different, out of the hundreds of possible magnetized white dwarfs that you could look at, that you assumed a particular mass and coupling. I guess it's not so sensitive to the mass and coupling, the ranking that you end up with, but yeah, do you want to say a couple of words about that?
Yeah, thanks for letting me point that out. So this calculation is the complicated probability calculation that I bored you guys with for 3 slides, and then a really simple luminosity calculation that Rafelt and company did in the 80s. And the luminosity calculation tells us that the Axion luminosity, the amount of energy coming out of the star in axions per unit time, is just proportional to the mass of the star. So that's a constant factor in the front. Wait, sorry. I think I'm answering the wrong question. We in the table, sorry, there's 2 things I want to say. One is that in the table, the stars have different masses.
Mm-hmm.
The signal goes like the mass to the first power. And we are folding that in when we do the ranking. But it doesn't really matter that much because the masses only vary from 1.3 to 0.8. So it's a factor.
Oh, sorry, when you said fiducial mass, you meant...
I meant Axion mass.
Axion. Oh, yeah, okay, no, so I'm talking about changing the Axion mass and that product of couplings.
Yeah, so that has to do with the fact that the limit is insensitive to the Axion mass at low mass. So for the ranking, we're essentially asking which star would give the strongest limit down here, rather than worrying about the types of things you're asking about.
Like we just said, they're going to move around and be star dependent, but these limits in the low mass region are kind of independent. Yeah.
And then the other important thing to say is that the coupling dependence is just also an overall factor.
Right.
So the whole, so it doesn't, I picked this fiducial number just to make the plot, just to make the table for you. But of course, if I rescale that number, I rescale the signals.
Mm-hmm. And so in that low mass region, just the ranking of these, of the limits you'll get from each of these different targets is going to be the same.
Mm-hmm. Yeah.
Okay, great. That's quite robust.
Yeah.
Thanks.
Okay. I'm seeing the time. Any last question?
Well, thanks for all the great questions.
Yeah, so then let's thank Andrew again, and we finish at least the official part, and everyone who wants to go